So, welcome to this lecture in scientific computing. Today we're going to look at two things. We are going to look at the built-in function library of Python. So, what built-in functionality there is in Python that you can use. The second part will be on object-oriented programming. I already touched upon this, that everything in Python is an object. And today I'm going to briefly go into how you can create your own objects and classes of objects, because that can be useful to understand how Python is built and other libraries are also constructed. So first, we're going to look at system functions. So in most languages, or most when you're programming, developing software, you need to access the system, properties of the system that you're running. And one important thing is something called environment variables. So in Windows, for example, and Linux, there is an environment variable called path that is contains a list of the paths that we will be searching for executable. There could also be other variables controlling different aspects of the system. To access these variables in Python, you start by using the import OS here. So the OS module in Python contains a lot of the system functions that you need to interact with the system. So we import that module, and the environment variables are stored in a dictionary, of course, because it's Python. So in this case here, we can, for example, print os.environment. This is the dictionary that is contained inside the OS module, and we can access it using the name of the environment variable we want to access. We can also loop over the variables like this. So for variable in OS environment, and then print out the variable name and also the value of that specific environment variable. It's also possible within the executing code, set additional environment variables. So here I just like a dictionary, I assign the value to give the name of the variable here, and then assign a new value. And then you can see it's available here. This environment variable will not be available when the program finishes. So that is added for the executable script only, and when that terminates, that variable is gone. This variable also contains all the variables that are available when you start the script. So it looks at the system environment and adds those to this dictionary. This can be used for example, if you want to execute other code from Python, you can set some certain variables so that that process can be found, or that script can find these some variables. So it's important to interact with other stuff in the system. So you can run this here. So the first line here, this is the path variable. You can see here, this is, I'm running on a Windows machine. This notebook is running on a Google server somewhere running Linux. So in this case here, you can see you get a Linux search path here. And the Linux search path is delimited by colons. And you can see here all the paths that are searched when you're trying to execute a command on the command line. It's searched all these paths here. And on Windows, you use backslash and the semicolon to delimit the path. But it's just a variable in the system. And then you can see here that we loop over and print out everything. You can see there is a lot of environment variables available on a Linux machine and also on Windows. So I think there is, so host name here is where I'm executing. There can also be a home variable where you're executing from. That's also available on Windows. So these are system variables, and can be useful to be able to interact with them in Python. There's also a way of accessing the path directly without going through the environment variables. So there is a system function called getExecPath, which provides you with a list of the paths that it will search for executables. So it's a bit simpler to it's more system independent because it's just list the paths. There is no delimiter between, so it's on Windows. It will also display a list like this. Also, when you're running your script, and you start the script from a command line like Python and your script, the directory where you are located is called the current working directory. So when you start here, you can query the current working directory by using the getCVD command. That will print the current directory. You can change the current working directory by using the change here command. And then you can see also that it changes when you run it. And that can be useful, for example, if you have your code is, you have the process data and you have them in folders. You can switch into that folder, execute some code, switch back again using this command. So here you can see, now it's a bit strange, I'm running on a cloud server somewhere, but here apparently I'm running in the content directory. And if I do ... I go one directory up, and I'm in the root directory here. Then I go back again by using the old variable. I store a string from the original here, so I can get back again. So every Python script has a working directory. If you're working in Visual Studio Code, in the terminal window shows you where you are, or if you open the directory in Visual Studio Code, it's a directory that is the current working directory. In Spider, you can see there is also, it's displayed in the user interface, the current working directory. But you can query that from within your script using the getCVD. Another important task that is often required is to be able to query the files that are in the directory. So you're running your script. I want to check for all files with an extension of something. I need to do that. So in this case here, I just touched test file that created an empty file. So this function is using the list dir. That will list all the files in the current working directory. So if I print here, it will print all the things. Then you can also query here using os.path.isdir if it's a directory or if it's a file. So list here lists everything in a directory, regardless of if it's a file or a directory. So you can see here that this is the first 3 files here, config, test file, sample data. And then I loop over here and I have config is a directory, test file is a file. There's a catalog called sample data here as well. So you can also interact with the environment or the work with directories in different ways. So you have, for example, change dir we have seen before. There's make dir for creating a new directory. It's the same thing if you type the command make dir in the command line. But this is works on all platforms, so you don't have to know the specific command that is executed. So this is the preferable way then. Using a system command and calling the shell behind it. This creates the directory. Yeah, so here you can, here is also a rename. So you can rename a file. So this is the file I want to rename. This is a new name. And you can also remove directories, remove files. However, remove can't remove directories that are not empty. So there is another run called remove, and there is another library to use if you want to erase all the files inside. It's also possible to query the information on the files using a special function called scan dir. Then you can loop over here entry in it. So this will loop over this direct result that it gets back. And then here you have entry name, file name, path, if it's a directory, if it's a file. So you notice here that you can do many things in different ways in Python. So it's depending on what you need and require, you can do it in multiple ways. But usually there are functions built in to do most things that you want to do. You can also walk recursively using the OS walk function here that will traverse a directory structure. It walks all the files that are in my directory. You can query file information using the stat command here. So I do it for stat info file, stat info dir, and I print it out, and I can get information on when the file was created. A lot of very system I/O related information here. Let's see what I can do. So you have this A time, modification time, access time, modification time, and let's see, current time. No, creation time, sorry. You can also, there is a function for working with the path. So apps path expands a path. So if you have some, a dot means current directory. If you call the system apps path on this, it will actually expand it to an absolute path that contains home, user, and text, for example. Base name will return this part of the file name. Dir name will return this part of the file name. Then you can also check for if a file exists. If you have a Unix or Linux machine, you have this tilde sign here. That is your home directory or user directory. An expand user will return the full file name, a full search path for home directory. You can also check what we did before with stat. You can do get access time, get modification time, get creation time. And there's also a get size, query the size of the file. You can also check if something is absolute, is apps, is it file. I have already showed that before. This final one here is actually good to know. So, for example, if you want to do a Python file that will work on Windows and Linux. So Windows has the path like this with backslashes, and Linux has the forward slashes. If you want to combine a directory with a file name, you can use the join statement, and it will do that if it's running on Linux, it will add a forward slash. If you're running on a Windows machine, it will use backslash. So it will platform independent join the directory with the file name, which can be very useful to make it so that you don't have to do one version for Windows and one for Linux. Another nice thing is using split here. That will split your file path in a directory and a file name. On a Windows, you can use split drive. They will also return the drive letter. And you can get the extension of the file using split ext. Here you can see here that I have split here is directory file name, and then it doesn't work here, but here you can see that I can split with an extension here. So you have the file name here, test, and then .txt here. So also when you're working with paths, if you're doing some scientific computing, try to always work with relative paths, so that when you're running from a directory, your code does not reference your home, username, and so on. It's just said, okay, I have all my image files in the image directory. Then I say, okay, I use image slash. I don't need to know the other things, but because you're working from a current working directory and relative to that, then the code is more easy to move. You can also use the environment variable for controlling where to find and find files and directories and stuff like that as well, or configuration file, but never have fixed file names, in fact, fixed directories with your username in it. Then there is a special library called pathlib. I don't go through that too much. It's an object-oriented way of manipulating paths. Temporary files. So in many computational codes, you need to create files that are only valid for the run of your program when you do the computation. You're not interested in keeping the files after the computation, but you need to create a file. And in Python, there are many ways of doing this. So there is a function called, or a module called temp file. And in that, there is something called make secure temporary file. And what happens then if you run this, it will return you a file object and the path to that file. And you can also check here if it's actual file. So here I have an example of how to use it. So I use my try here with open temp file object here as temp file. I open the file, I write to it, and I read it, and I finally remove it because I don't need it after I have used it. So you can see here it creates on a Linux machine, the temporary files are in the temp directory. On the Windows, I think they are in a different location. But it will create a random file name like this. It's a file, and this is written to the file, and I remove it, and after that, the file is not there anymore. But here I have to do many steps to kind of create the file, work with it, and then I have to remove it myself. It's actually possible to create an object instead called temporary file, as temp file, which handles all that stuff for you. So you can just write to it and see it, and when you're done and the file is closed, it's also removed automatically. So you can see here, at this point here, the file does not longer exist. And I know that many system administrators are very happy when you do things like this, that it also automatically cleans up after the run. But this is a more automatic way of doing it. Something that is also a common task when you write Python script is to be able to run programs from Python. So, for example, you have a calculation program, simulation program written in Fortran, available as a binary. You can start that from Python. You can generate input data to the file and start your program, wait for it to finish, and then afterwards continue computing the results from that program. So one module you can do this is something called subprocess. And here you can import a module and use subprocess run. And I provide which command here is the first parameter, and the parameters to that command. The result here has a return code property. So if everything executed okay, the return code will be 0. If something happened, usually it's not non-zero. But here you don't get any output, it just runs, then it's just check that it's run okay. This process is also blocking. So when you call run, it will wait there until the function has finished, and then continue executing it. So if you want to have a look at the output from the command, you can do an alternate version of this. So you can give the command as you would give it on the terminal. So this ls for list files, all the attributes. This tells it I want to execute in a shell environment, so in a terminal like bash or in a command line window in Windows. And what I do here is that I assign standard output, which is when you print, it goes out to the terminal, that's standard out. And then I said I want to have that as a pipe. I want to send that output not directly out to the terminal, but into a pipe. And this is something that handles the new lines in a platform independent way. So when I run this, you can still check the return code, but here you have another property called standard out, and that is all the output that the program generated. So I just cache that as a string, and then I can process it here as well. I can go in and check if there are some error messages or something else in this one here. So if everything run here, you should have a listing of all the files in the directory. So let's run this and see what happens. So here you can see here that process returns 0. Output data here, this one here, is a string of all the output that the program generates. So if you have a simulation code that generates output, it will go into this standard output string. And then you can process that after you have executed the program. However, sometimes you don't want to wait for the process to finish. You want, for example, to do some other processing here. You want to run the code and it can run simultaneously with something else. Then you have to use a command called popen. That starts the program running beside your own program. So it's running in parallel to your own code, Python code. You get an object P here that is actually the process object. So you have a handle to the running program. So this is running here, and at some point I need to wait for the result of that program running. Then I do p.wait here. The program stops here, my program Python here stops here, waits until this program finishes, and then continues here. It's difficult to see here because because I don't cache any output here. It just waits and continues when the program is finished. To illustrate a bit better, I will use a more long-running task here. So there is a very important command in Linux called sleep, and I will sleep for 5 seconds. So I will start up a sleep process that is running for 5 seconds. I can then check here during the run if p-poll is none, it's still running. So in my program here, I'm waiting for the other process to finish. I just go run. I do time sleep here. So I'm waiting inside my Python code until p-poll is not none. So when this is done, I have the data here. I can query it again. You see here, it waits. It should be done there. So it started up the sleep here, running next to my Python code. And I'm waiting here in my Python code here, constantly checking every second, is the process finished? Is the process finished? And if it's finished, it goes out of the while loop here and prints out the result. Now you can do the same thing here, use popen here. But so in this case, to get some output here, I just list the files and I call sleep4. I execute this in a shell and I redirect output here, standard output using a pipe. I also redirect. So there are several pipes that we use. So there is also something called standard error. So some processes, they send their error output to a separate stream, and you can redirect that as well. And when you're done here, you need to do some more. So you need to talk to the process here and ask for the standard output and standard error strings here. So this will collect the data that has been collected during the run and assign it to standard output and standard error. So let's see what happens if we run this code here. Wait 4 seconds. So it waited for the process here, collected information, and printed out the standard output here. So I got the same thing. And the standard error was not available here. But what we could try is if we change here to LSU or something. Now you can see here that now I didn't get any standard output, but I got an error here because it couldn't find the LSU command. And that goes to that special stream for error messages. I just have to change it back again. You can also, to make sure that you close the processes, you can use the same principle as for opening files. So you can do with subprocess p open. That makes sure that everything is closed when the process terminates. Basically, it's the same thing as before, just that it's more robust. What I usually do in my code is that I create to don't have to litter the code with a lot of these process things. I usually create a function called execute with output. And then I have my command here that I want to execute. And inside this function, I do all this stuff, collect the output and return it. If I don't get any data, I just return none. And I have kind of made a simple way of executing commands quickly in Python. Here you can see how I use it. Output executes with output, ls, and then do some processing of the output from the command. Like that. So we have more complex applications. It is often a good idea to implement some kind of logging functionality. That when you're running your program, you can output messages with different information statuses. So usually you have debug, info, warning, error, critical. And what you can do then is in your program, you can configure how much output you want to see. So if you're debugging a code, you can enable, I want to see both information and debug levels, and it will print all those messages. But if you're running it in production, perhaps I only want to see the warning or errors. So Python has a built-in logging module called logging. And then here you can set it up using set level logging debug that will display everything. You do some logging here, and then you set level error and do some logging here again. So this will print out different way. First, it will print out everything. In this error here, will only print out error levels or higher. Okay. There are different streams in Python, that's why this doesn't work. I will comment out the first one here. So I do it like this. So setting the debug level here will print out all the messages that I printed out here. So this is the way the default logging looks like. So you have the level here. Who is logging this? In this case, it's root because the cloud instance is running as administrator. And this is the message that comes out. You can configure it to print out dates and other stuff as well. But if I change here to want to log only errors or run this, it will only print out the messages that are from error and above. So error is lower than critical. So other messages are ignored. You can also look to a file. No, sorry, you can create your own logger using this command here. So you can get a log here, and you can set specific settings for this logger, and then you can process along here and use that as the instead of the global logging functions. You can also change the formatting. So if I want to format, you use, for example, time and other things here, you can configure it using the formatting strings like this. And you assign this in the basic config of the logging module. And if you run this, okay, if you run this on a normal console, it will change. There's something, I don't know, we're running this in the cloud. It will produce the same logging information as before. Okay, another thing you want to often do in your code is to be able to sort stuff. So, no, sorry, not sort stuff, storing stuff. So you have data that you want to store. For example, it could be configuration files for your program, other things that you want to store and read back. So Python has a built-in data structure called built-in library called JSON that will store things using JavaScript object notation. There's a structured way of storing fields in a text file. So I have my data here. It's a dictionary of a lot of things. And I can open a file here, my data.json as a file, and I can do json.dump. So then you give your dictionary and the file, and it will write that file down with that structure. You can also do it other way around. So you can do open a file for reading my file, and I can do json.load, and I load it into a different variable this time. So it will load from the file and create the same data structure I had before here, automatically here. So let's see what happens if we use this. So you can see here that this is the copy of my data. It's very similar to what I have up here. So this is one here. And I read it back. So this is a dictionary again. And you can see here that if I look at the data on the file, it's very similar to a Python dictionary. So this is a very nice way of actually writing quite complex information to disk without inventing your own file format. So, and then you can query this data structure as a dictionary to see if there is data in that data structure that you want to use. You can also modify the data. So as long as you don't remove dictionary keys, you can add stuff to it without creating a new version of the file format. So you can have it's quite powerful. It's also used very often in web applications or other tools that are online services that you can send a request to JSON, you can get JSON request back. So this is something can be useful for certain situations. You can also get these things into strings. So in this case here, I can use the dump s command or dump to string, and it will store the JSON in the string. And you can print it out here, and you can do the same thing, take the string and convert it to data structure again. So this can be, for example, useful for if you have a web application here, and you want to send this data over to somewhere else, you can convert it to a string, send it over the internet as a string. On the other side, I catch the string, and I convert it back to data structure in Python. You can see here I can, these are the strings that I created. You can also, if you don't want to have this kind of compact version of everything in a single row, you can actually dump string. You sort keys here, so it sorts the key in order, and you can also indent by 4, so you can get a more readable version of the JSON structure. Then you get something like this. You have the keys in sorted order, A here, and then it's indented here, so you can read it quite easily. This could be, for example, a configuration file for a computation code. But you set up the variables, you read it in, and you get a dictionary you can directly use in Python for controlling your calculations or your data parsing. There is also another format that is built into Python from the beginning. It's called Pickle. And that is the standard way. Before JSON, there was Pickle. And Pickle is a binary format. JSON is a text-based format. Same thing here. It's very similar to the JSON here. You have a dictionary here. You write WB here for, I want to write in binary. And I do pickle, dump, my file object, my data and my file object. And you can pickle load in the other direction, read binary like this. It's probably more compact if you want to write larger data structures. Works the same way. This is just for pickle comes in different versions, so you can actually there is a second parameter here to select the protocol. So if you have an older version of the pickle format, you can select the format here. If you want this data, so I would use pickle more for temporary data storage. If you want more structured storage for not a huge amount of data, I would go JSON, because JSON is standardized data protocol. Pickle is more, it's a binary file, it's not always readable in every system. You can also do pickle to string. And you can see here that this binary format is when I do pickle dumps here, you see I get the binary string. So it's not very readable. But you can do that. And the same thing as I've said before, if you pickle to a string, you can send it over the internet, for example, using a point-to-point communication. And then I get the string back here, and I go back and I get the data structure again. Python also has built-in support for data archiving compression. So, for example, here you can use something called tar files, which is commonly found like zip files on Windows. Those are used on Unix-based machines. It's an old file format that comes from tape archive. So it was the format that was used to write on tape storage. But it has been used to create archives of the directory structures. So first, to illustrate here, I will download some files that I can use. And the nice thing with the tar module here, so it's available in the tar file module, and I import it as TF. I can create a tar file object just like I create a file. So I have a myarchive.tar.gc. So usually the extension is .tar.gc because the tar is the file format that is non-compressed, and usually you run it through zip to make it more smaller. And that is handled automatically by these tar files. You don't have to do all this. If you just specify .tar.gc, it will do that automatically. Write as mytar. Then I can add files to it. mytar.add the second image here. Then I can go another way around. I can open this file for reading, and I can ask my tar object here, what are the names in the archive? So get names, members. I can extract here, extract all, give it a directory name. You can list things in the archive. You can see here if I printed the get names here. I have build first image. I have the second image. I can print the. No, so these are. So there are every image is stored in a tar info object here, which is this members here, and I can get more information on those. I can extract. Here I also list the actual file names that are contained in the archive. And if I look in my directory now, You can see here I have I extracted them to my tar all. So there's a directory here. And if I look in that one, you can see that I extracted all the files in that directory. You also have a very similar module called zip file for handling zip files. Unfortunately, they decided that it was not useful to have the same API. So here you call write instead of add. But basically, it works in the same way. So you have a name list here to list the files in it. You can get information about the image. You can extract all like the other ones, and so on. So let's see here if we can. So basically, it works the same. So it's very useful in Python to look into runtime library, check if there is modules that you can use instead of using system functions for doing this that are in your operating system. Usually there are a lot of ways of doing things from the runtime library in Python. The advantage of using the runtime library is platform independent. So regardless of a Linux, Mac, or a Windows machine, it works the same way. Yeah, you can also do other interesting stuff here. So let's say I have a data structure here. I dump it to a string. Then I print the length of my string. And then I call the clib library. So clib is also a Python module that can do compression, but on memory, for example. So I take my data dump here, which is a string. I compress it, I get a compressed string back. I do a length of that string. Hopefully that should be shorter than this one. Then I can do clib decompress. I take my compressed data in here, I get uncompressed out, and I do pickle load from that here, and it should be the same as I had before. So let's do all the steps and see if it works. So you can see here that the original data is 2,825 bytes. The compressed data is 1,926, so it worked. And then I uncompressed it, and I got my data structure back again. So this could be useful if you want to transfer data or somewhere, and you want to make it smaller. You can use clib internal here to compress it in memory before you send it away. This we already did. So before we go to the next session, there are some special file formats that is good to know. So in many programs, you use configuration files to configure the settings of a program. That's called configuration file. And a well-known file format is the ini files. I think they started with original Windows, that the configuration file for Windows was stored in ini files. The structure of an ini file is that you have sections limited with the square bracket and the name. Then there is a group of variables. Then there is another section, group of variables, another section, group of variables. And you can, so in this case here, I just open the file and I write this file down. And here you also can see that this triple quote, the strings here, I use this as a template for my configuration file. So I just open write this entire string to disk. So I have a config file. Then we have a module called config parser, which is also built in module in Python to parse configuration files. So in this case here, we can read config parser, config read, specify the configuration file. You can query which sections are available in the configuration files. You can access them using a dictionary method here. So this will go to the section bitbucket.org and the user. You can loop over here for section in front of sections and then print out information inside the configuration file. And you can also write it out again. Here you can see I can get my data here from this file. Another file format that is useful and used in very scientific context is the CSV file, or comma separated files. Let's see. So, and there is a module called CSV. So you can open here CSV file object here, and then you can CSV reader. And you can set it here to which delimiter the file has. And then you can print the data here. So it will. So it will basically look at the file, create lists, and you can. It's very simple module here, but I think most of this you can do completely on your own. And you can also use the load text in NumPy to do this if you have NumPy structures. So that was a bit on the built-in functions. So let's do 10 minutes. So now we'll do some fun stuff. So object-oriented programming. So object-oriented programming is a concept where you combine data and code in a single entity. And usually objects often describe nouns such as point, circle, equation, string, file, and so on. And you interact with objects by sending messages. And the messages are the verb that you kind of communicate with the object if you want it to do something. And in Python, the verbs are usually methods or functions that are attached to the object. So an object also has methods, the verbs, which define what the object can do. It also has properties that describe attributes of the object. It could be the color of the object or some other properties. In computation, you usually have some attributes that describe the properties of physical objects as well in your objects. Objects are described by something called a class. So you don't create objects directly, you create them by specifying, I want to create an object of a certain class. And the class is the blueprint for an object. So it describes what goes into an object. And before we had object-oriented programming, we used function-based programming. So we had functions and data structures. And if we want to create a point, we call the function here with parameters, and we got something back here, data structure of a point, for example. And if we want to move this point, we pass the point data structure into the function, write some additional parameters, and let the function manipulate the data structure. Same thing here, 0 point data structure, and so on. There is no connection between the functions and the data. So it's you pass the data into the function manipulates the data and so on, but it's the functions kind of are standalone. And if we run this code here, just defines the functions. And first I create a point. And basically that is just a list of X and Y coordinates. I can move the coordinates, and then I pass the point variable P into my move point function, and it modifies the point. I can set the point, so I can change the values in the point. So you pass along a data structure. The data structure can be anything that the create point decides it to be. But the idea is that you pass along the data, manipulate the data using standalone functions. And here also print the points. So we want to do the same thing using object-oriented programming. we need to define a blueprint for a point. And we do that using the class declaration here. Class, and this is the point, the name of this class, and you can compare it to data structure like a string, double, floating point. This is our point blueprint. And most classes needs to be initialized. It has to be created. Attributes has to be created to the object. And that is done by the init function. And the init function is a special Python function because it has 2 underscores here and 2 underscores here. So this is part of the language. This is called when you create an object of a class point. The first thing it's called is this function here that will initialize the attributes of the objects, in this case x and y, to 0. So when you create a point, the default position 0. And the self x and self y, those are called instance attributes. And those are unique for each instance. So every time you create a new object, that new object will have an additional set of x and y attributes. It's like you're using a stamp. You can stamp out multiple objects, or you can, like a cookie cutter, you can cut out multiple cookies from the same shape. And this is the point, is the kind of template of blueprint for that. So how do you create objects? So if I execute this now here, nothing will happen. It just defines the class point. And you create a new point by specifying p, that's our variable, and I want to have a point object. This creation here will call the init method automatically and assign x and y attributes to the p object. Same thing here, I create a q object of type point. Q will have x and y attributes added to it automatically. So if I run this code here, I can access my attributes by specifying x, y, x, y. So both of my p and q have x and y attributes. They are not the same. They are different, unique to each object. So in this case, we can create a list of points. All of them have unique x and y coordinates. You can also assign attributes. So px equals to 1.0, py 2.0. And you can see here also the uniqueness between the objects here. But q is not changed. It still has 0 and 0. But p and x has 1.0 and 2.0. One of the key cornerstones of object orientation is encapsulation. Is that the data structure internally in an object should be hidden from the user of the object. And in this case, the attributes are quite visible. There are x variables attached to the object directly. So suppose we want to store the point in the database somewhere else. We can't provide direct access to x and y. We need to kind of provide a way of accessing x and y coordinate that doesn't manipulate the internal data structure themselves. So usually what you do then, you add methods for accessing the data. And in Python, there is no real way to hide things from the user or an object. But there is one convention here. If you put 2 double underscores here before the attribute value, this value is not accessible by anybody. So you can actually not access it from if you create a point object here, you can't access these attributes. So this is kind of the most useless object you can create because you can't access its internal data. So x and y are now hidden from us. And so how do we, I can show you how it actually works. So if I run this, creates a point, and I try to do the same thing I did before, Python is very unhappy with it. Point actually has no attribute x because I hid it away using the double underscore. So now it's a private internal variable. And one way of accessing the internal data structure is using access methods. And also, you could suppose that you could do this, the underscore, but that is also not, doesn't work. So using the double underscore, hides the variables to the user of the object. So one way of doing providing access to the internal method is using methods. So this is very common in Java and other languages that are object-oriented, that you create private variables and then you have set and get methods to set your data and access your data. So in this case, I have setX. I also have a convenience function set, which sets both of them at the same time. And now I can do this. I can create a point here, set the internal data structure to 12 and 13. I can also call set here to change the internal variables here by using this method here. And internally, it will set the variables. You can do set X and set Y as well. And then, of course, you need to access the data as well. So one way of doing it is providing an X and Y function that will return the internal variable value out to through the function. And now we have a class here that you could change the entire implementation here. So, for example, the underscore X could be some data in a database that you call from some that is on the internet, for example. But the interface to the object is still set X, set Y, X and Y. But you hide the internal implementation. In this case, it's kind of very simple, trivial, but it could be a more complex implementation here, stored somewhere else. But you still have the same interface to all the functions. So now we have get set method, so we can actually both set the internal data structure and we can also get out the internal data structure. But wouldn't it be really nice if we can use this simple way of accessing attributes that we have just p.x equal to something and still have this internal data structure hidden? And Python has borrowed from several other languages in this case. So properties is some notion that was created in, I think it was Object Pascal in the beginning, was ported over to C#, and Python also got properties. And properties is a way of creating variables that can be accessed just like a direct attribute variable, but it calls function for setting it, calls function for getting the data. So if we look at the point here again, we keep all of our set and get method here just like before. But at the end here, we add a special declaration x equals a property. And the first argument here is the method to retrieve the x property, so get x. So when you read this attribute here, it will call get x automatically. If you assign x, it will call set x. And then same thing with get y and get set y. So this hides everything, and we can use the object just like before, but with an internal implement, with all the data structure hidden internally. So now the code becomes like this. So we have create the point. Now we can do p.x equals to 42, p.y equals 84. And what happens here is that when you assign here, it will call the methods, the set x, the set y. And here it will call get x, get y. But this much nicer way of actually using the objects. You can see here when px here, it's a set x, set y. It's called get x, get y. Internally, you hide the data. Externally, you make the object really easy to use. And my philosophy with this is that don't prematurely create a lot of get set methods, because Python has this way of going from object attributes to properties. You can change an object attribute to the property later on, and the user of that object will not notice that you have gone through from an internal attribute directly to function calls, get set methods. So that's why you can really create really simple objects from the beginning. And if you want to store them in a database, you just implement them as properties, and you can still use the same code. So that's the beauty of the properties, that you can really, you don't have to do a lot of coding from the beginning. Just do a conceptual class and then adds functionality later on. Then there's actually something that makes it even easier to use properties. So there is a notion, I won't get too deep in this, there is something called decorators in Python. And decorators are special ways of generating code automatically for you. So by specifying, for example, here, this keyword at property here, and then having a function with a name of your property. So defx here, and then you do return the internal value here. That will automatically create this property declaration. You don't have to do more of this. This will automatically be a property that you can read. Then you can have something called an X-setter. This will add the ability to write to the property. But this is the only thing that is required to implement. Then you get a read-only property. If you add this, you can also write to the property. They have to be in this order. So you have to first define the property and then the setter. So here I have done it for this clause here. So you see here, I don't have to have this property declaration here below. And now I can use the clause just like before. And you can see here that it calls setter for x, setter for y, property of x, property of y. So just by adding this add property, you get this functionality automatically. And if you want something that is to be read-only, just omit the implementation of the setter decorator. So that was a lot of properties. So let's get to the verbs or the instance methods. So instance method is the way the verbs that interact with objects. Because the data structures are hidden inside, the methods can be quite short. You don't have to pass the data along. You can just say very short move, but the internal things you don't have to pass along. You can do clear if you want a clear data structure. So what do we need for verbs in a point? It would be nice if we can move a point. So you can see here that we have, this is a move method. And also something to note that all object methods always has to start with the self parameter. And the self parameter is something I always in this course have, it's most difficult to explain what it is. But self is the actual object that you use. So if you create an object and you want to move that object, self will become the actual object to be moved. So self is a reference to the actual object. Because you can't, when you design a class, you can't say that this is a, you have to have some kind of reference to the actual object that has been created. So in this case here, when I move the point reference comes in here, and I add self.x plus equals to dx here. So modify the internal object variable that is the self variable here. But the nice thing is that you never have to, when you have an object, you don't have to provide this self. So when you use the object, you don't, so in this case here, I create the points here, but the move method here, I don't have to specify self, because the self is actually this one here. And it is transferred automatically by Python here and inserted here. In this case, self is P1. It goes into the move here, comes in here. So this is actually P1 here, P1 here. Is that, you comprehend that? Could understand what I mean? So self is a reference to the actual object. And you can see here also, I mean, in it also has a self, but when you create an object, you never give this one here. You give X and Y. But here you need to assign the internal variables to the right object. That is the self reference. So now I can use the object here, so I can call move. and it will move the P0 object. P1 will move the P1 object. And hopefully, so all objects start at 0, 0. So if you move it 10 by 20, it should have a position of 10, 20 here. Let's see to check out. And I said before, sometimes you need to copy an object. We can do that as well. So in this case here, I want to copy the data from the values from another object here. Self is my own object, the current object. This is the object I want to copy from. So self.x equals to p.x. Self.y is p.y. You see here, I can't assign underscore x or p because it's not visible. So I need to use the properties here to assign the values. So here I can do like this, create 2 points, move them, and I want to copy a P0. P1 copies. So now there should be. Now you can see here that P1 was 1010, and I copied P1. Oh, sorry, P0 is 1010, and then I go P copy from P0, and P1 is now 1010. Then there are a lot of, so you have already seen some of the special instance methods. So one of them is the init method. And that is always called when you create an object. That is the method that's called when you create a new object. There is also a str object that is used to convert any object to a printable form with print. So for example, if I create a point here and just try to print it out, Python is nice to print every object in any way. So all objects in Python are based on the main class object. An object has some rudimentary functionality for printing itself, but because it doesn't know what a point object is, it just prints out, okay, it's located in the main module, and it is located at this memory address. Not so very useful to know. So what we want to do is we want to add functionality to be able to print our point object in a comprehensible form to the screen or to a string. And what we can do then is add this str method to our object. So in this case here, we add this special method here, str. And what we need to do now is convert our internal attributes here to a string that we return back. And usually when we do printing, we want to print it in a way that you can create this object like a constructor here. So we do point parentheses, and we print our internal attributes here and return that string. You can do whatever you want here. It's not strictly needed to do this, but this is a convention that most other classes in Python use. So let's define this one. And now printing should look much nicer. So now I can print my object here, and it actually knows how to print itself out, and in a readable form as well. So that's a nice method. There are some other methods as well. So there is also a method for when you delete an object. There is also all the operators in Python. For example, add, subtract is also a special method that you can implement. So you can actually implement your own algebra using these special methods. And that is how NumPy does some of these things, that it implements some of these special functions to do this. So any class you create in Python has the same value or same level as in any other data type in Python. So when you have created your own, you can do stuff like this. You can do append to a list. In this case, I create 10 random points to this list. Just to note that there is some ways of doing loops in Python for creating lists directly. So you can create a list like this, point random for I in range 10. This will create the list in one go. Here you will kind of have to loop 10 times. This is somewhat faster, but perhaps a bit more unreadable to people. And because we now have an str method to our point, we can easily print all our points. So P here will just print here, we'll call the str method on our point and then print out our points like this. And these are also references again. So like as I told before, that variables in Python are references to data. If you do P2 equals to P0, and P3 to P1, P2 is equivalent to P0. So they will point to the same point data structure. And we can see if we use our ID function here, that it should be true. So you can see here that these two are the same as these two here. So let's say now we can't create a world of just points. We need to kind of be able to create other objects. So for example, if we want to create more geometric shapes, which share the same attributes as point, for example, the position. So a circle, for example, it can inherit most of its functionality from the point. And in Python, you can create a circle that inherits from point by using first the new class, and in the parentheses, you specify which class it should inherit its functionality from. But now we have a problem here. So we need to be able to, when we create a circle, it also has to initialize the point, the data structure from the point. And we do that in an init method here. So in the init method, we have our x and y, just like we had for a point, but we also have a radius now. So we add an additional parameter here. But now we have to pass that x and y over to the init method of the point. And we do that using the super here. So the super function returns you the base class of circle. So in this case, it will be point. So super here, then we call init x and y, and that means that we call the constructor or the initialization method of the class above. Make sure that these x and y are available to us. So now we have everything constructed from the point side. Now we have to add attributes or internal data structures for our circle. In this case, it's an R. So we do self underscore R, that is our radius, and we assign R here from the input parameter here. And if I have these equal signs here, that means that I don't have to specify them as a user. I can do create a circle, and the default values will be 0, 0, and 1. And I have a property R here that returns the self R. I have a setter here for R, like this. I also have a copy from, and I also updated our string value here. So in this case here, I print out circle instead of point. And I do like this. So copy from here, I call first the point, copy from, and then I copy, set my R here for the incoming circle here. So you can see here in our PC, CR, so the C has an R property. I can use move here, both on the point, but also on the circle, because it inherits all the functions from the base class. And the print function here should print point and circle, because both of them have their own str method implemented. So Python knows that this is a circle, and it will call this circle function. So this was inherited classes. There is also a group of classes called composite classes. And this is a very common way of constructing classes. And that is a class that contains objects of other classes. And it could be, for example, you have a car class that contains 4 wheels. So there's a field object. There are no inheritance relationship from a car to a wheel. So the separate objects. But the composite class car has references to the wheels and the engine and so on. So in our geometrical world here, we have a line, for example. And line has 2 points. So we have a class here, line. Doesn't inherit from point because it doesn't have a position. You could have, if you have a drawing program that you have a line that actually can move around, then you can actually inherit from point as well. But that is a design choice. But if you have a line that references 2 points, we have 2 internal variables underscore P0, P1. We create those points here internally. So now we have a composite object consisting of 2 points. And we have a property here, and property P0 and property P1. Now they are read-only, so you cannot reassign the point. The line always have 2 points that are unique. You can change the x and y position, but the instances are read-only. And then I have a print statement here that prints out line from cell P0, C P1. So yeah. Let's define that. So now you can create the line. I can assign x value of P0, y value of P0, x value of 1. Does this work? No. So this is, here's the error here. You can't assign it because you only have read-only property. So it only returns an instance. There is no setter. That's why you can't set attribute because it's read-only. So, but you can actually, this is also a design choice. You could have a design choice that you say that the line always has its own points. They can't be changed. You can also have a line that you can update the references to the points. And it's not too much difference. You just add a setter for each of these ones. And now we can do like this. So we can create new points and we can assign P0, P1 to different points. But there could be situations that you don't want the user to be able to change the instances. Then you don't create a setter. You just create a property, nothing else. And then, of course, we have a line. We need a property called length to calculate the length. That's very easy. We create a read-only property because you can't change the length if you have 2 points. It's fixed. So we have a read-only property length, which we calculate the length of the distance between these points. And then you can run it like this. And then you print line.length, just like it would be a read-only attribute. But when you call this, it will always have the right length because it will call the length calculation function here. Calculate the length. So the final part I want to discuss is something called polymorphism. And that means that if you have a class hierarchy with multiple classes inherited from a base class, Python can figure out which method to call automatically. That means also that you can have, if you have a list of different objects that are inherited from the same base class, and you have re-implemented some of the methods, Python will know which one has been updated and called out automatically. So it determines which method to call depending on the data type. And this is really interesting here because now I have this shapes list here. I had a point, a circle, a line, I had a floating point number, and I had an integer and a string. And I call print all them out. You can see it works. It will know which str method to call. So in this case here, point has an str method, and it looks at this here, and the print statement looks for the correct str to call. If it's not available in the point clause, it goes one step up. Is there an str method in the object clause above? And it continues up until it finds the correct one. And that is the polymorphism. An interesting thing is, what is a floating point? Does the floating point value have an str method? And in Python it has. So every object, even a floating point, an integer, is an object with these methods. I will show you this just here in the next example. So what does 42, print 42 actually mean? It's actually this. So 42.str will return a string of 42. You can also do, if we have, I'll copy this code here. Now I will change to, I will remove these ones here because they are not, they don't inherit from point or, also remove line here. So point and circle both inherit from point. And I can do shape.move like this. So Python will check here. Okay, this is a shape coming in here. Okay, is there a move method in the circle instance? No. Is there a move instance in the point circle? Yes. I will call the move method on the point object. So we kind of look at and call the correct one. Had there be a special move method on the circle, it would find that move method and call that first. So in that way, you can override all the methods, and Python will automatically figure out which method to call. Okay. It doesn't make sense to print a function without return value. And you can see here for doing. So you can see here that we call the right ones, and it also added the positions to the shapes. So object orientation is you have already used it. The string is an object. You use the split mesh method of the string to return a split version of string. That was object-oriented programming. So a lot of Python functionality relies on objects. Then it's also important to not go too wild with object orientation. You should kind of keep a middle ground. So for example, if you do a particle system, you can of course do thousands of particles using the Python objects, which is really, really inefficient. But you could have a particle system that uses NumPy arrays for storing the particles. Then you create a nice class that you can instantiate the particle system with, but it has efficient internal data structures for handling the points. So this is also something to think about when doing object orientation. Don't go too deep in the nested inheritance charts. Often composite objects is much more efficient to use than having a long hierarchical list of inheritance. Sometimes, for example, in user interface design, we will see that later when we come to Qt. In user interface, there is a natural inheritance chart. So you have Windows section is, for example, rectangular area in the window, and then you have a button that inherits from a rectangular. You have other data structure can group objects. There is natural inheritance chain there, which is Qt uses very nicely to don't really implement a lot of functionality. And it's also inheritance can also be used to avoid rewriting a lot of code. But as I said, keep it kind of in the middle ground. And often when you do object orientation, before writing code, write it on paper. Find all the nouns. It could be, for example, in structural mechanics, you have beams, you have bars, you have trusses. Those are natural classes that you can define. There are points that could be an object as well, or class. And then find the verbs, what you want to do with the object. For the tutorial, for the workshop, or the next schedule, I will do a demo on object or the program that's a little bit more graphical. So we will implement same thing here in text, but using graphics. So you can see the benefits of using objects in a graphical setting. So that was all for today. Any questions? I will put all these notebooks available for you so you can experiment yourself. So you can run them in your own computer or on Colab and try them out. Okay, thank you.